Hi, welcome back, grade 12s. So, this is the last part of our number patterns, sequences, and series, and this is going to be on geometric patterns. Okay, I have the worst handwriting. Geometric patterns, and these geometric patterns are somewhat similar to arithmetic patterns. However, instead of having a common difference, they have a common ratio. So if we jot this down to a way that we actually mean business is, we recall from an arithmetic number pattern, we can have an arbitrary pattern A, B, C, D, E, F, just a standard pattern. And if you're subtracting all these values, you'd actually have a certain key difference that is the same, hence we call it the common difference. However, for geometric patterns, you're not going to be subtracting them, you're going to be dividing them. That's how you're going to get the common. And this is no longer called a common difference, it's now called a common ratio. Ratio means divide essentially. So that's how you would get the common ratio R. You would do this by taking your second term divided by your first term. And this should be the very same thing as you taking your third term divided by a second term, fourth term divided by third, and so on and so forth until you die. So that's it. And then for the nth term of a geometric pattern, the nth term of a geometric pattern takes the skeleton of A multiplied by R to the n minus 1. Okay. And it also has a sum, and its sum is also somewhat interesting, and we're going to look at all of these and do some example questions, of course, so you don't have to really stress much about trying to gallop everything in a day. So let me grab this for you. um yes, there we go. Okay, so for your sum of values in sum of n terms, it's not going to be the same as your arithmetic. However, this one is going to be, there's actually two ways of putting this one, in fact. So your sum is going to be A multiplied by R to the n minus 1 over R minus 1. This is one way of calculating your sum. However, some people can go around swapping these things. So it's the very same thing. This is the same thing as using A multiplied by 1 minus R to the n over 1 minus R. You can swap the R and the ones and stuff. Okay, as long as you have the same thing at the bottom. And please, your R can never ever be 1. Otherwise, you'd have 1 minus 1 on your denominator, and that gives you a 0. And we all know what happens if you try to divide by 0. That is dangerous mathematics. So you just can't do that. Anyways, then we also need to understand the concept of the sum to infinity. As much as we can have a pattern that ends somewhere, however, with these geometric patterns, we can have a sum that ends nowhere. It goes all the way up until infinity. Okay, so that's the concept of sum to infinity. So yes, you can calculate the sum of values in an infinite series. And sum of values in an infinite series is just a over 1 minus r. There's nothing much fancy about that. It's just a over 1 minus r. But hold on. There's something interesting here. There's something called convergence. There's something called convergence that arises when you're working with these things. Convergence, the idea of convergence just says that as much as I keep adding values to my sum up until infinity, what is happening to my sum? Is my sum also approaching infinity, or is it getting less and moving away from infinity? So if it converges, then my sum is actually increasing towards a certain value, towards infinity. However, if it diverges, then it will be coming back. It's as if I'm taking away from the sum to such an extent. So its limit is actually moving away from infinity. That's the idea. And whenever they talk about convergence, just remember that a geometric pattern will always converge if your R is between negative 1 and 1. Okay, so your r has to be greater than -1 but less than +1. That's how you know that it converges. And also remember, I mean, come on guys, look there, your r cannot be anything that's not that. See, nonetheless, we came here for difficult stuff, so let's do some questions on these geometric patterns. So I'm going to grab a question out of the question papers. Let me see which one I can take here. I want one which is a little interesting. Before I do that, there's a couple of things I need to keep in mind. Let's do a brain example. I'm gonna think up of an example. So here, let's just imagine we have the arbitrary case. Let's say we have the pattern 3. Let me just make up a pattern here. 3 multiplied by 3 should be like 9, and 9 multiplied by 3. I'm honestly just making up a pattern here for the sake of testing. 9 multiplied by 3 should be like 27, and 27 multiplied by 3 should be like 81. So 27, 81, 27, 81, and it keeps going. Let's just suppose we're given this pattern. Let's find the nth term in this pattern. Okay, so first things first, you're going to find your r, and your r, it happens after you divide, not subtract this time. So I'm actually going to have the 9 divided by the 3, and this gives me 3. So that's a common ratio, easy stuff. That is, baby stuff. Then I go down to Tn. We know Tn is supposed to be a multiplied by r to the n minus 1 for a geometric pattern, and the a is the first term. This is 3 multiplied by my r, common ratio of 3, n minus 1. Done. I leave it there. Do not try to multiply the 3 and the 3. The other 3 has a power and the other one doesn't. Don't try funny business. You just leave it like that. Okay. Then it ends just like that. Then we we have to understand how to calculate the sum, obviously. So for the sum of values, let's suppose I'm gonna end it there. Let's calculate the sum of the first 4 values. Okay, so we're calculating s of 4. So if you're calculating the sum of the first 4 values in a geometric sequence, I've provided that formula, and I've given it in 2 different ways. I've given it as a to the r, right? A to the r, n minus not a n minus 1, a r to the n minus 1 over r minus 1, or you can give it as a multiplied by 1 minus r to the n over 1 minus r. Either of these two, we'll test them both out for the sake of being open there. So a is the first term, and the first term is 3. Okay, then we'll just open that bracket. Then r is the common ratio. We got a common ratio of 3. Okay, then n, well, the number of values I'm trying to add up are 4. I'm trying to find the first 4 values. Minus 1 divided by r, which is 3, minus 1. Okay, and this adds up to what? Let's see. All right, so I'm just gonna grab that calculator and sum this up and just enter it into the calculator as is. So I've got a 3 multiplied by 3 to the 4th minus 1, and I'll close off that bracket, and then this is a 3 minus 1, and this gives us 120. So nothing fancy there. So we get 120 for the sum of those values. So I'm just getting 120. And then you're probably imagining, what if I use this one? Well, if you use this one, then your substitution would be like as follows. You'd have a 3 for the a, 1 minus, and then your r would be 3 still, and your n, you're still summing up the first 4, divided by 1 minus r, which is 3. And if we use the calculator for this, let me just grab the calculator, and let's put it on this side for the sake of visibility. Okay, so for this, we're still summing up as is, so I still have 3 multiplied by 1 minus 3 to the 4th, and this is all then divided by 1 minus 3. we still get 120. So regardless, you still get 120. Okay, easy as pie, just like the arithmetic number patterns. Then let's get the concept. Actually, let's see. Does this pattern converge? Well, let's think it through. Remember what convergence means. Convergence means that my r has to be between -1 and 1. However, the r that I got is 3. So clearly this pattern does not converge. That's it with convergence. But let's consider, just like arithmetic number patterns, the case where we do not have successive terms. So I know that I gave you a pattern which is successive, but let me try and extend it. So we've got 3, 9, 27, 81. After 81 should be 243, and after 243 should be 729. So we've got 243 and 729. So we've got 3, 9, 27, 81, 243, and 729. These are the values of this pattern, but let's just imagine that I didn't give you all these values. Let's just cancel out some values. So I'm just gonna take some of these values to give them to you, and then we'll work with them from there. Let's imagine that I gave you the second term. So that's 1, 2, 3, 4, 5. Let's imagine I gave you the second term and the fifth term, and then I want you to find the general formula for this, and then maybe some stuff after that. So I'm just going to give you the second term, and there's 1, 2, 3, 4, 5, and the fifth term. So these are non-successive terms, they don't follow each other. So you have to have a way to work around this, just like we did in arithmetic number patterns. Okay, so first things first, we're going to begin by means of using simultaneous equation. Okay, and the way in which we do the simultaneous equation is the same way we did with the arithmetic. I would form two formulas, one for this one and the other one for that one. That's very much it. So I know that t of n is equals to a r to the n minus 1. I know this. So I'm going to make the substitution for this one, okay, for term number 2. So I know the tn should be 9, and the a is the first term. I honestly don't know that. Then the r, I don't know that. However, I know the n. The n is 2. That's the term number, minus 1. Then I'm going to clean this out to become 9, which is equal to AR. Then 2 minus 1 is, well, it's just 1, so I don't need to bother writing that. Then for the other one, I still know that Tn is equals to ARn minus 1. Then the Tn, I know this to be 243. I don't know the first term. I also don't know the R, but I know the N to be 5. So that's a 5 minus 1. So I've got a 243 here, and then A R 5 minus 1 is A 4. Okay, then I'm going to pick one of these two and make A or R the subject of the formula. Okay, so what I'm gonna do is let's just pick this one for the sake of simplicity. So let's just suppose I take that one and make A the subject of the formula, just to avoid these to the power r's and all that. So if I make A the subject of the formula, I'm going to have n over r is equal to A. I just divided both sides by r. Now I have A being the subject of the formula. Then I'm going to substitute it into that one. So I'm going to have 243 equal to, instead of A, I'm going to have a 9 over r. Okay, and then I have multiplied by r, which is this r to the fourth. However, I'm going to then simplify this and then solve for r. So 243 is going to be equal to 9, and then these are going to cancel, and I'm going to have a 3 left. So actually I have a 9r cubed. This is getting cool. Then I'm going to divide both sides by 9. So 243. So 243 divided by 9. So 243 divided by 9. That should give us 27. Okay. So we get 27. 27 is equals to r cube. Okay. And then to remove the cube, I'm going to cube root both sides. So then I'll end up with an R of, which I'm gonna check now with the calculator. So we got cube root, so I'm gonna do that with a 3 of 27, and that just gives us a 3. Okay, so for the sake of those who don't know how I did that with the calculator, there is the calculator, and I'm essentially just doing the cube root. Because of the 3, I'm going to do a cube root. So I'm going to do that, get the 3, and then pull out the 27, and then I should get 3. Alright, so I get 3 for R, so R is equal to 3. Then to get back my A, I'll take this and pump it back into that equation. Then this just becomes 9 over 3 is equals to A, of which 9 over 3, A becomes just 3. Pretty interesting, pretty sick, right? Okay, of course I'm going to show you a formula for this one as well. So let me just jot down what we got. We got an R of 3 and an A of 3. Okay, so we're gonna just leave that aside. Then I'm just going to clear this entire area and then show you the way to check that answer by using a formula. So then the formula to use in the case of geometric patterns is, you would say Tn, oh not Tn, no, R, my bad, the common ratio to the power of y minus x is equals to ay over ax. Okay, and remember I told you this before, y is just the largest term number, y is just the largest y is the largest term number. Okay, so let's identify the largest term number. So we've got our r, and I'm about to put in the y. The largest term number is a 5 as opposed to the 2, so that's just a 5 minus, and then obviously x should be the smallest term number. Then ay is going to be the value, that's 243, divided by the value of the ax, which is 9. Then now I have to solve for r. So 5 minus 2, that's 543, and then 243 divided by 9. I'm gonna use the calculator for that explicit calculation. So I'm gonna put it aside there. Okay, so for this we got a 243 divided by 9, and we get 27. This is beginning to look a little familiar. We get a 27 for that. We get a 27, and then we're going to cube root both sides. So if we cube root both sides, we're going to be doing the cube root of 27. So the cube root of 27, so I'm going to do that. I know I've done this calculation before, but for the sake of simplicity, we're going to get 3. So the cube root of 27 is 3. We get an R of 3. Then how do we get our A? Well, the same way we did with arithmetic. You would pick one of these terms that you're given and then work with them. So let's just suppose, for the sake of making things a little complicated, let's use this one. Okay, so I'm gonna make the substitution for that one. So I know that Tn is equals to a r to the n minus 1. However, I know the Tn to be 243. Then the a is unknown. R, I just found the r to be 3. To the n for that is a 5 minus 1. Then I just simplify things from there. 243 is equals to a multiplied by 3, and then 5 minus 1 is a 4. Then 3 to the 4th, gonna grab a calculator. 3 to the 4th is 81. So we get an 81 for 3 to the 4th there. So this is a multiplied by 81, and here we've got 243. And then to get a, we'll divide both sides by 81. So that's going to be 243 divided by 81, and we get a 3. We get a 3 for our value of A. That is that one done. And that's how you work with non-successive terms when you are working on geometric patterns. All right, so we need a past paper. We have to get a past paper. So I've got a couple of these ones, and I noticed that this is honestly just too simple. So I'm gonna set this aside, and then I'm gonna get us a beautiful question paper. So okay, all right, let's grab this one. This one looks interesting. All right, so okay, yes, copy, and then let's get this on the board. Okay, we may not need that too. Okay, so we're gonna do this one for the rest of the video. And this is out of November 2015. This is the final paper, obviously paper 1. So let's begin that. So first things first, we're going to look at the first question there. So we're given this geometric pattern 10 5, 10 5, 2,5, 1,25, and it goes on until thy kingdom come. Then they want you to calculate the fifth term of this pattern. How dumb can they get? But anyways, let's look at it. So first things first, we would find the common ratio. So we'll divide these two. We're not multiplying, it's a geometric pattern. Okay, so I'm gonna grab the calculator there, and then we're going to divide there. So to divide those, that's just 10 divided by 5. I don't even know why I'm doing this. Actually, it's 5 divided by 10, not 10 divided by 5. So 5 divided by 10 is just a half, and that's 0.5. That's what we get for our common ratio. We get that 1 over 2. So this 1 over 2 that we just found, this is what we're going to use to find the fifth term. So to find the fifth, this is what term 1, term 2, term 3, term 4, and then term 5 is after that. So all I'm doing is dividing by a half each time. Okay, so it's actually getting smaller and smaller. So I'm dividing by half each time. So I'm going to get to that 1,25 and divide it by half. So I'm going to grab the calculator and then take the 1,25 and divide it by a half. And a half is 0.5. Like that. You can even put it as a fraction. You still end up with the same answer. So we get a 5 over 2, which is 2,5. That's what we get for the next term then. We get a 2,5 for that. And then the nth term of the pattern, okay, determine the nth term Tn in terms of n. That's just easy stuff. So we begin by finding the ratio, which we already just found. Here's the common ratio. So I'm just going to jump into the formula. So Tn is equals to a by r to the n minus 1. What is the a? A is the first term, so that's just a 10. Multiplied by r, common ratio, well, that's a half. To the power of what? N minus 1. Done. It's in terms of n, and is the general formula. That's it. Then they're saying explain why it converges. Oh, sounds cool. Okay, for this, to explain why it converges, remember I said converges means that my r is between -1 and 1. And this is just 2 marks. So you just need to explain, actually you don't need to explain anything, you just need to write that r is equals to 0, 0,5. Therefore, the r is not less than, it's actually greater than -1 and less than 1. You've just proved that it converges. Done. Sounds sweet? Sounds beautiful. Then determine the sum to infinity minus the sum of n, where sum of n is the sum of n terms of the sequence. Ah, ha, ha, ha. This sounds twisted. This sounds very twisted. But let's look at it. Let's look at it. So let's get rid of that. And let's play around with this one. Okay. So for this question, the thing we must determine what is s to infinity minus s to n. So s to infinity minus s to n in the form a b to the n where s of n is that. So let's first figure out what is s to infinity. So what we know is in a geometric sequence, s to infinity is equal to a divided by 1 minus r. This is the sum to infinity. And the first term, a, is 10 divided by 1 minus, and what is r? Well, r is the common ratio, and that's just 0, 0.5. Done. So can I simplify this? Let me just grab my calculator and it will tell me if I can actually simplify things or not. I'm just going to type that in as it is and see if I need to simplify this any further. So that's just 1 minus a half. I just get a 20 for that. Let me just write it down. Maybe this will come in handy. So I get a 20 for the sum to infinity. So that's 20. Let's get some space and let's figure out what is the sum of n terms. So the sum of n, we know that sum of n can be represented by ir to the n minus 1 over r minus 1. However you do it, we still end up with the same answer, so don't worry much if you use the other one, which has 1 minus r to the n. It's still okay. Then for the value of a, we're getting at 10. And then what's our r? Well, that's our common ratio. That's 0, 0.5 to the n minus 1 divided by r. What is r? Well, our r is 0, 0.5 and then minus 1 there. And then can I simplify this? Well, yes, I believe I can. If I play around with this, actually, let me just jot down that this thing is actually 20. We'll need that. So I just actually need the space here. Well, actually, I can just scroll down. I don't know why I had to complicate life there. But anyways, can we simplify this? Let's grab the calculator and let's see. One thing I know for sure is that I can take the half minus 1 and simplify that now. So I'm gonna do that. So what is a half minus 1? That should be like 3 over 2. Actually, it's negative half. What's wrong with me? Anyways, negative half. So I'm gonna get a negative half for the denominator. So I'm gonna do that. Alright. So I get a negative half for my denominator there. So I've got 10 and then 0, 0.5 n minus 1. And then I have a negative 0, 0.5 there. And then I can make the division of this and that. I mean, maths allows me to do that, so why not? So I'm going to grab the calculator and see what is 10 divided by a negative half. 10 divided by a negative half should be negative 5. I think. Okay, let's see. So 10 divided by negative 0.5. Ooh, too bad. That's negative 20. Okay, we'll set that aside. That's just negative 20. So I actually get a negative 20 there. So what I'm going to get is negative 20 multiplied by 0, 0.5, 0, 0.5 to the n minus 1 and close that off. So this is it. Then let's go back to the expression that we were given to work with. The expression we're given to work with says the sum to infinity minus the sum of n, and then I have to give it in the form of a b to the n. Okay, let's do that. So I have the sum to infinity gave me 20 minus the sum of n gave me negative 20, right? It gave me negative 20. So I'm just going to do a sort of a huge denomination there, and then I've got 0, 0.5 to the n minus 1. Okay, and we'll just close the big bracket there as well. Okay, then let me just simplify this one a little bit further. So I still have 20 minus, okay, and then this negative 20 minus this thing there, this is just going to be I'm still inside this bracket, negative 20 multiplied by 0, 0.5 to the n, and the negative 20 multiplied by negative 1 is positive 20. Then let's multiply in this negative. To multiply in this negative, it would multiply by that, so we have 20 Okay, so we have 20 multiplied by that net, that would be positive 20 by 0, 0.5 n plus 20, right? Then remember the form that we're supposed to give our answer in. We're supposed to give it in the a b to the n form. So what we then realize is, whoa, 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 what am I doing? Wait, this negative, and where did I get the positive 20? This actually brings it, this is a negative. I made a mistake there. So let's trace back. So negative 20 multiplied by that gave us this. Then the very same negative 20 multiplied by that should be a positive 20. However, when the negative comes in, it should come back through and make it a negative. This is a negative 20 there. Yes. Oops. So we should grab the pen. So we should be having a negative 20 right there. Okay, then negative 20 multiplied by negative 20 is 0. So I'm actually left with 20 multiplied by 0, 0.5 to the n. And now it's actually in the form of a b to the n. Hee sexy maths. Beautiful. And that is that question done and dusted. And once again, such questions like these can get a little tricky and you can lose yourself within it. So they get better with practice. So go ahead and practice these things a little bit more. And then I'll see you guys within the next chapter. See you guys.